This video on Newton's laws, and what we're going to do now is solve some problems concerning Newton's laws of motion. And I already have the files open here, and let's see what we're going to look at first. Of course, what we're going to focus on is just the Newton's second law, which is force equals ma. Force equals ma, which is just the same as m dv over dt, which is the same as dp over dt. Yes, and the first problem is just saying if f is equal to 3 over 2v plus 1. So this force is a function of velocity. As you can see there's a variable for velocity in it. So this is f, the force, which is this expression. M is 2 kg, the mass, okay, which is the mass of this body. And the body is initially moving with velocity 2 meters per second. So this is the initial velocity at t equals 0. This is what you mean. Whenever you hear the word initially, then you must consider time as 0. So t is 0 and the object is moving with 2 meters per second. Now find t, the time when v is equal to 6 meters per second. Now what we're trying to find is the velocity, or should I say the instantaneous velocity, when rather the time when v is 6 meters per second. That's what we've been told to find here. Now, looking at the solution, we know that force is the product of mass and acceleration, which is just force is 3 over 2v plus 1 on the left is equal to ma. M is just 2, acceleration is dv over dt. So what do we do now? We rearrange the terms such that this function containing v is associated with the dv part here. As you can see, it's just about rearranging such that we can write it in this way: 2v plus 1 over 3. This is just done by dividing the left side by this expression itself and the right side with this same expression, so that it becomes in this form, and also dividing both sides by 2 so that we get a 1 over 2 on the left. So this is just a matter of rearranging these terms. And what you're going to have is the integral of 1 over 2 dt must be equal to the integral of this expression dv. Okay. And from here, you can even rearrange it further by multiplying this with a 2 there, cross multiplying. This 3 goes this side, this 2 multiplies with this expression inside. We get this expression, just a matter of rearranging. And integrating this 3 dt, you get 3t here, must be equal to, integrating this expression, we'll have 2v squared plus v plus c. So this is a constant of integration. Now here we can apply the initial conditions. We know that at t equals 0, v is equal to 2 meters per second. So velocity is 2 meters per second. So this should be v is equal to 2, not 6. So this is an error here. This is 2. This should be 2 here. Yes, this should be 2. So that should be 2 here, and not this expression which is appearing in it. So let me just use a marker, or is it a pen, to just change this. First let's do this. Remove this 6 and say 2. So this should be 2. Okay, the marker is too too much. Okay, let's do this. Let's do this. Paint it. Let's move it. And we'll put the thickness is just too much. Okay, taking it back here. And we have a 2. So this should be 2 meters a second. Yes, like that. So this is what we have. At t equals 0, v equals 2 meters per second. That's what we have at time equals 0. Now, applying these initial conditions in this expression, we can find the value of the constant c. So at t equals 0, putting a 0 here, we get 0 on the left. And v equals 2 meters per second. Whatever is v, put a 2. You have this plus that. Then you finally find that c is equal to negative 12. Finding that, you can replace this c, which is negative 12, back in the original expression. Plug in this c in this expression, we can make t the subject to the formula, and what we'll have is this expression here. We'll have this expression for time, and this is what we have after making t the subject of the formula in this expression and substituting for v equals 6. So remember, wherever there is v here, we put 6. Wherever there is v, we put 6, as you can see here. Why we're putting 6? Because they want us to find time when v is 6 meters per second. So that's what we do and get 24 seconds. Alright, looking at the second question. A particle of mass 2 moves in a force field depending on time t given by F equals this expression here, 24t squared I plus 36t minus 16j minus 12t k hat. So this is the force for this particle of mass 2. Now, assuming that at t equals 0, this is the initial conditions. The particle is located at r0 equals 3I minus j plus 4k. So at t equals 0, the position is this. And the velocity is v0. Of course, a naught is used to represent initial conditions. v0 equals 6I plus 15j minus 8k. Now the question is to find the velocity and the position at any time. So I want to find the position and velocity of this particle at any time. So if you look at this question, it's a bit different because we've been given an expression which is in vector form with basis unit vectors I, j, k. Otherwise, the process is still the same. So I'll try to find the velocity and the position at any time. So how do we get velocity? Okay, using second law, force equals mass times acceleration, which is m dv over dt. So we're going to take the force as it is given, put it on the left. So this is the force, which is just this, is equal to m, which is 2, and the acceleration is just dv over dt. Okay, and right in that, we can divide the left and the right side by 2 so that we have this expression here. Okay, so this is what we're having, and we can of course make this dt cross to this side and multiply with this expression so that we have an expression in this form. Doing that, we integrate here, there, the left side integrates also the right side. So the left side is being integrated with respect to v, the right side is integrated with respect to t. So integrating the left side, we just remain with v is equal to, now integrating the right side with time, we have 40 to the power 3i plus 90 squared minus 8t j minus 3t squared k plus c. This is a constant vector. As you can see, there's an arrow because what we're dealing with now is a vector expression here. So the constant also has to be a vector with an arrow. Okay, so now from here, this point, we can even use the initial conditions, which is at t is 0, v is just v naught, and it is 6i plus 15j minus 8k hat. This is this thing we've been given here, which is this expression here. V naught is equal to 6i 15j minus 8k, which is just this expression. Now, when you substitute these initial conditions into this equation, you're going to find out that when you put t equals 0 in this expression, this whole part of this expression will vanish. This part starting from this point all the way up to this point will vanish to 0 because t is 0. And our v, which is v naught, will just be 6i plus 15j minus 8k, which will just be equal to this c. That's why we have in c equals 6i plus 15j minus 8k. Okay, so since we have our c, we can now take it back in our original expression for v. So taking this c and replacing it on this part, we're going to have this expression for velocity. Now you get this expression after rearranging and taking the like terms in I. You see this 6i will pair with this 40 to the power 3i. This 15j will pair with this part with the j. That's why we're having this. And this minus 8k hat will pair with this part with the k hat. And you're getting this expression. So this is the velocity. This is the velocity. And now looking at the position at any time. So we found the velocity at any time. Now let's find the position at any time. So to find the position, we use the expression for velocity. This same expression is what we're going to use to find the velocity. Okay, so now what we know is that v is just dr over dt. So v is dr over dt. That is something which is known, which we've done before already. So v dr over dt is just this expression here, and from here we can multiply the right with the right and left with dt, so that you get this kind of an expression, and then you integrate both sides. Integrating both sides, we're going to remain with r being equal to this expression, which is this here, because integral of the r is just r, and you get this expression here as r being equal to this part here. So now moving on to integrate this part, we'll have r equals t to the power 4 plus 60 I plus 3t cubed minus 4t squared plus 15tj minus t to the power 3 plus 8t plus c1. So here I've used a difference letter to represent the arbitrary constant, which is c vector c. I've placed it with a subscript 1 here plus c1. So when you integrate this 40 to the power 3, you're getting this. When you integrate this 6, you're getting this. Integrate this 90 squared, you're getting this expression, this, you're getting that, this, that, and so on and so forth. Integration is something you know, I don't have to teach you that. So at t equals 0, okay, at t equals 0, r is equal to r naught, and r naught is just 3i minus j plus 4k. This is something which has been given already. So using these initial conditions in this expression, replacing for t equals 0 here, you're going to remain with c being equal to this expression, this r naught. That's why you're getting c1 is equal to 3I minus j plus 4k. Why? Because wherever there is r here, we replace with the initial condition for r, which is this expression. And you find that C1 is just this part here. Okay, so if you do that and find C1 is this, when you press for C1 in this part here, and rearranging the terms in I, the terms in J, and the terms in K, what we're going to have is an expression which is looking like this: 2 to the power 4 plus 60 plus 3I plus, of course, you see there's this part already, but when we include this term with a j, which is just minus 1, we're going to have this expression with the minus 1. And this part here is the part in the k hat. So mind you, there should be a k hat here. Or let me just do it quickly. Let's just do that. And yeah, let's do this. And add a k here. Okay. Yeah, let's just do that. So this should be with a k like that. Okay. Yeah, that should be with a k hat like that. So these are the terms with in the basis vector k hats in the direction of k hat. And from our C1 here, we know that the part with a k hat basis vector is 4. This is what has been added here. And of course, it's having a minus here because when this negative multiplies with this negative, it will become positive as it is there. All right, so this is our expression for the position at any time. This is the position at any time. Now let's look at question 3. A constant force F acting on a particle of mass m changes the velocity from v1 to v2. So a constant force F acting on a particle of mass m changes the velocity from v1 to v2 in time tau. Okay, now prove that F is equal to m v2 minus v1 over tau. And does this result in a hold if force is variable? So does this result hold if we have a variable force? And explain. What we mean by a variable force is just maybe a force which is dependent on some variable, like maybe a force dependent on time, a force dependent on velocity or something. But this is a force which is just a constant. So now let's see what we're going to have in the solution. Of course, Newton's second law is being applied. We know force is ma, which is equal to m dv over dt. Okay. Now, what we know is that when we say force is equal to m dv over dt, we can rearrange the terms to say f dt, just multiplying dt crossing that side, cross multiplying, of course. We'll have f dt equals m dv. And then integrating on both sides and rearranging, swapping the left for the right side. When we swap, the left side goes to the right and the right goes to the left, we're going to have this. And then we integrate both sides. Now, integrating will have limits of integration. What limits of integration are we having? This particle is changing from v1 to v2, meaning that v1 is the initial velocity and v2 is the final velocity. Okay, so we're getting the limits from v1 to v2 and f dt. Okay, the integral of f dt, we're having time running from 0 to tau. So time is running from 0 to tau, this tau here. So integrating this expression, we're going to take m, a constant, out of the integral, write it, and then integrate dv, which is just a v, with the limits running from v1 to v2, being equal to f, okay, F, we'll take it out since it's a constant force. We'll take it out and integrate. Of course, okay, yes. We take it out of the integral and integrate the t on its own. So integral of the t is just t. Okay, integral of the t is just t. In fact, here I should have a t. Yeah, I should have a t here. And just okay. Yeah, let's just do this. There should be a t here because I've integrated this. I factored out f and integrated the t. So we should have a t here. We should have a t there. Yes, this t is multiplying with f, so that our limits, which are running, of course, from 0 to tau. Our time is tau here in the question. Now, using these limits, substituting into, for starting with the left side, we substitute for v, the upper limit minus the lower limit. That's what you have, v2 minus v1, which is equal to f. Just like for time, we substitute the upper minus the lower, which is tau minus this 0 here. And we have this expression. And what we have is m v2 minus v1, which is equal to f tau. Okay, f tau. We're having this expression. From this part, we can make f the subject of the formula, and we'll have m v2 minus v1 over tau. And we're having this as our expression, which we've proved as asked in the question. We've shown this. Now, does the result in A hold if the force is variable? Explain. So what will happen if we had a variable force? So the answer does not hold. So no, it does not hold. It cannot hold because if force was a variable, for example, a function of some variable like time, we would not have got the result in A. We wouldn't have got this result in A. So no, this force cannot be variable and the answer wouldn't have held up. So yeah. So for now, we'll end on this question, and in the next video, we'll look at question 4 and question 5. So thanks for joining me, and I'll see you in the next video. Bye.